Hi, today I'll be talking about PPD, or Personalized Preference Fine-Tuning of Diffusion Models. Diffusion models have achieved great success in image generation tasks, with high-quality aesthetic images and high fidelity with instruction following. Several SOTA models are diffusion-based, such as DALL-E and Imagine, and following language, recent prior work has been focused on aligning these models with human preferences, as seen in works such as Diffusion DPO and DPOK. But is instruction following sufficient enough to do personalization? Many alignment objectives involve the Bradley-Terry model. However, this is a little bit limiting because these models align to the general population of users, and thus marginalize out individuals. In practice, this assumption can fail, as individuals can have many diverse preferences, such as the style, color, lighting, and other visual attributes of an image that they care about. An alternative approach is that individuals can state their preferences, but this has two different limitations. Firstly, as seen in class, the gap between stated and revealed preferences is quite large, and people may have like a biased view or share a better version of themselves that doesn't actually lead to ground truth personalization. Additionally, the short context of clip-based text-to-image diffusion models is also limiting, preventing us to actually condition on individual users' preferences. We thus propose PPD, a method that can align diffusion models with individual level user preferences. Let's dive a little bit more into this. We'll first define the problem with a special form of the preference dataset, where each element in the dataset consists of a caption C, preferred and dispreferred images X's, and the user features U. We now define R as the reward of image X0 for caption C with a user with features U. Thus, we can now define the KL-constrained RL objective as the maximization of the expected reward with a term that allows you to preserve the KL between the current policy and the reference policy. Here, our policy has a closed form for a particular user following the DPO objective, where the policy is proportional to the reference policy weighted by the exponentiated reward weighted by temperature. Following diffusion DPO, we can derive the following objective for PPD. Note that the objective that is arrived upon is similar to the diffusion DPO objective, with the addition of U representing user features for each user. But what features should be conditioned on? It is unclear how to best parameterize the user features U. One approach that can be taken is to collect information from each user through surveying or other collection. However, these are very incomplete and biased, and also additionally expensive to collect. We alternatively propose a simpler approach, assuming access solely to the unique user identifier S to differentiate different users in a preference dataset that we represent now as the following tuple. We can now take two approaches to then construct our user features. One is through a one-hot encoding, where each individual identifier corresponds to a unique index and is thus transformed into a one-hot encoded vector. Additionally, we can consider few-shot conditioning on features from a particular user. These features include preferences that they might have labeled before, and thus we can encode them and form a user feature. Let's dive deeper into how we construct the few-shot embedding. We condition a VLM such as Lava 1 Vision with n preference pairs per user and extract an embedding from the VLM decoder's final layer hidden state. This embedding is reasonable to consider as the VLM is fine-tuned on sets of multiple images for general question answering. We additionally perform some initial validation by training a classifier to predict the user conditioned on few-shot preferences from each user. Here we find that the few-shot classifier significantly outperforms random chance, resulting in a reasonable embedding being formed. To then describe the full PPD framework, we first take a set of few-shot image pairs from user A, as shown on the left. We pass them through our VLM and generate a user profile with few-shot image pairs. While this generation occurs, we extract a user embedding that is then conditioned on through cross-attention with the encoder of the stable cascade stage C model. This allows us to train a personalized diffusion model. We first evaluate this framework in a synthetic user alignment situation. This is a didactic task where we study 3 synthetic users defined by 3 well-defined reward metrics. The first is CLIP for prompt image alignment. The second is aesthetics prediction for the visual appeal of images. And the third is HPSV2, which is an estimate of human preference. The user feature here is going to be the one-hot encoding that we first described for each user, and the data set is balanced across users. We compare against 3 different baselines: stable cascade, diffusion DPO, and SFT. And we finally study the interpolation of the user features to see if we can better control how each user is personalized to. Firstly, we look at win rates for each of the different users that we have. For each of them, we find a significant improvement over the baselines that we have discussed, such as stable cascade, diffusion DPO, and SFT. Next, we study the interpolation of different users by interpolating linearly between the one-hot encoding weights. Note that these were not trained at all because we trained on each individual user independently. However, we still see a smooth interpolation between each of the reward functions, resulting in an increase in prompt alignment through CLIP and a decrease through aesthetic quality as we move to the right, and an increase in the human preference score as we move to the top. Given the success in the synthetic alignment setting, we now move to a more realistic pick-a-pick dataset where we scale from 3 synthetic users to a filtered subset of 5K unique users in pick-a-pick. Here, we compare against the same set of baselines as the synthetic setting and additionally view the qualitative generations of our methods on different baselines. Here, the user condition features are now generated from the VLM on 4 in-context preference examples as seen on the right. Firstly, we look at the win rate, comparing stable cascade to our model on a generic user with held out captions, a user that is seen on held out captions, and an unseen user on held out captions. And in all 3 scenarios, we see a significant improvement from the base model. Next, we consider qualitative results. We consider the baselines diffusion DPO and stable cascade, along with appending a generated user profile to the caption as an augmentation. What we find is that PPD achieves closer alignment with the generated user profile, which is highlighted in green, but conditioned on this profile solely results in unintended image alterations, causing the image to disregard the caption itself, which is highlighted in red. PPD, in contrast, is able to both align well with the caption that the user requests for, as well as the profile of the user that has been synthetically generated. Thank you.